Hold on. And it's okay, recording.
All right. Hey everyone, welcome to today's session. I'm Ava.
Hello, everyone. Welcome. And I'm Ani Aiken.
Ariakan, before we start, I heard that you passed the ML Specialty Exam certification. Congratulations. How was that?
Appreciate that, Ava. Yes, thank you. It went well. And I would say, just like with transfer learning and machine learning, I found that my preparation for the associate level, the ML associate level exams, right? Uh, the even the AI practitioner exam, but mainly the machine learning engineer associate and the data engineer associates. Those helped me prepare for the ML specialty exam, since there is an overlap, especially in areas like SageMaker and data pipeline. However, Eva, as you know, the specialty exam does require deeper technical expertise, especially in machine learning on AWS, like that is leveraging AWS services for machine learning on AWS. And also having hands-on experience definitely makes the experience better.
Those are great tips for preparing for the exam. So it builds upon previous, exams that you have taken, which is kind of a good, hopeful note to add here. So congratulations again, Aniakan.
Absolutely. Thank you for that. And yeah, so today we are diving into feature engineering.
And
And yeah, we're going to go into feature engineering. So this is, as you all remember, this is part of the machine learning data processing lifecycle.
This is very cool. Oh, yeah, there you go. I see there you have that very helpful diagram, I think. So maybe the first question to ask Aniakan is what is a feature in feature engineering?
Yeah, great question. Yes, a feature is, well, first of all, you'll see it by several other names, right? You might see it as an referred to as an independent variable or a predictor variable, or even as a covariate. I've seen that in exam or question sets a lot. So a feature is any measurable attribute of your data, like age or temperature or even categorical values that you might have in your data.
Very interesting. So features are like the raw ingredients for our models. If we take a tabular data set, for example, a traditional data set, such as a CSV file, a feature is going to really equate to the column of useful information. Is this correct?
That's absolutely correct, right? In the, let's say, for example, we have a housing pricing data set, right? So in here, what do we see? We see things like square footage column. We see the number of bedrooms and whether or not it has a garage. Those are all features. So yes, in that context, a feature is a column of useful information, useful in the sense of helping a model make a prediction.
Very cool. Okay, so that speaks to the traditional structured data. If a feature is a column used to make a prediction, what about data that is not in columns? We talked about unstructured data. What do the feature look like in that space, which is a big one?
Absolutely, it is a big one and very interesting question. So yeah, so when text is in a data set like this, right, we can easily recognize a feature, but what if it isn't, like you said? So what if the text isn't structured like in this tabular data set? Our model still needs numerical features. Like we said, features are used to help the model make predictions. So even with unstructured data, we still need to identify and extract features so that we can turn it into something that a model can understand and make predictions with. So for example, yes, this is a simple sentence, right? The claim is missing required documentation. We can't use this raw text directly. Instead, we can use a technique, and one technique that we point to is what the technique of taking and converting these words, like individual words, into numerical vectors. And these vectors capture meaning and patterns. And then each word or sentence becomes a set of numbers, right? In traditional data, right? Again, we go back to that. Features are simple, they're simple columns, like number of bedrooms. In unstructured data, we convert the data into complex vectors representing not necessarily the word, but the word meaning.
Very interesting. So we're translating text into a mathematical language essentially that machines can understand, and where each number in the vector is going to represent a different aspect of the word or sentence meaning, correct?
Yeah, and that's a great way to put it. In the sentence, the claim is missing required documentation. You can't feed that directly into a model. Well, yeah, actually, there are models that can accept text input directly. However, all models ultimately need numerical data to work with. So even when you input raw text, the model has to convert it into numbers internally. So these numerical representations capture the meanings of the text and become the features the model uses. So let's see an example of a vectorization technique. Right. This is called bag of words vectorization technique. So let's apply this vectorization technique to this sentence here on the top left. So bag of words vectorization is a method for pre-processing and converting text data into numerical format that the machine learning algorithms can understand and process. And so let's take a look. When we apply that vectorization model, or the bag of words vectorization model, to that sentence or those sentences, first we create the vocabulary, from all of the unique words. So we convert that to this vocabulary. I love this movie is bad, great acting in. Then the bag of words vectors are created for each sentence by counting word occurrences. Right? So we take it through the vectorization step. And then the resulting vectors would be this. Right. So Ava, what do you think? What are some of the things you can notice? What are some of the observations of this process?
Yeah, it's very interesting to see this technique, bag of words, cool name as well. Each document is now represented as it looks like a 9-dimensional vector, and those are going to be sparse vectors, which means that they contain many zeros. So the word order information appears to be lost here.
That is exactly right. And each number represents the frequency of that word in the sentence. Yeah, so this is a simple, yet it's an effective way for many natural language processing tasks to be done, like a task like document classification and spam detection.
All right, very interesting. So features are not just columns like number bedrooms, they can also be vectors that represent patterns, meanings, and signals in text. I'm beginning to understand why there is all this fuss about feature engineering.
That's exactly right. Yeah, good feature engineering, where we are selecting, we're transforming, we are creating and extracting features, can significantly boost your model's performance. It can reduce training time. It can help you avoid pitfalls like overfitting.
Yeah, there is a lot to explore there: feature selection, transformation, creation, extraction.
Yes. Yeah, and in this episode, we introduce the concept of feature engineering, and we'll explore feature selection. The others we'll cover in future episodes.
Sounds good, Anyakan. So you also mentioned overfitting. We talked about that in the last episode, I believe. There are this is where the model is going to learn a noise in the training data so well that it fails to make a good prediction in the new data, correct?
Exactly. Yeah, overfitting happens when your model memorizes irrelevant quirks instead of the true patterns. And Eva, you gave us a great analogy in the last episode of this, where one studies a test by memorizing the exam questions verbatim. They will see these same questions in exam and do well and ace it. However, if they get new questions, they may not do so well.
Yeah, exactly. Feature engineering is going to help strip away the noise of irrelevant information, is going to ensure the model, or you if you're studying, not you and Yakin because you passed your exam, but the rest of us truly learn the underlying concepts. So your learning will transfer to new related questions. Now, there is also the concept of underfitting, which is the opposite. This is when we have too few features, or maybe the features are oversimplified, and this can lead to this underfitting phenomenon. One solution here is to create more informative features. There are other solutions as well. Great. So let's get into the feature selection next. What is it and how do we do it?
Yeah, absolutely. Feature selection is all about picking the most informative features. It simplifies your model. It cuts training time. It fights the curse of dimensionality, right? When there are too many features, and that can confuse any algorithm.
The curse of dimensionality. That sounds scary. In simple terms, as you add more features or dimensions, the space your data lives in is going to grow so much that the points are going to become sparse, and it's going to be hard for the algorithm to extract meaningful patterns from the data. And this is going to increase the risk of overfitting.
Yeah, very cool. And here's a scenario to bring this home. You're trying to find your car in a parking lot, and let's say you didn't remember where you parked. If you had only one dimension, that might be like searching through one row of cars, right? You could find your car pretty easily there. What if you had two dimensions? Well, let's say that's like searching through a whole parking lot section. It's a bit more difficult, however, it's still doable. Many dimension, on the other hand, that's like searching through all parking lots in a city block. And the space grows exponentially as you add dimensions.
Okay, so I think we all understand now why dimensionality is a problem, or you might even say a curse. What methods can we use to select the most important features to avoid having too many of them in our model, Onyeka?
Yeah, and there are three major approaches that we'll talk about. We have, first of all, the filter method. Filter methods are simple statistical tests to remove unnecessary features before training, right? They look at how features relate to one another and to what we're trying to predict. For example, we can remove features that don't change much or are too similar to other features. SageMaker has tools that can help with this, right, Ava?
Yes, that's right. We're going to see
Okay,
some data wrangler in SageMaker shortly, actually.
very cool. Looking forward to that. The other feature, the other method that we can point to is what's called the wrapper method. Yeah. So the wrapper method is another feature that we can use to combat this. And the wrapper method is where we use a predictive model to test different feature sets. Right. And this is like running repeated model experiments to find the best group of features for your model. Right. And one popular technique is called RFE, recursive feature elimination. It works by training a model with all the features, ranking those features by importance, and removing the least important feature, and then repeating this until we have the desired number of features. So while this method is very thorough and can find important relationships between features, it takes time and computation cycles to run. However, The good news is that if you're using AWS, you can leverage, guess what? SageMaker.
SageMaker.
Exactly, to automate this process and handle large amounts of data efficiently. And then we have the embedded method. Yes, we have the embedded method. And this folds feature selection directly into the model training process. And we can talk about, first one, the lasso method, or the lasso L1 regularization method. So this adds an absolute value penalty to your feature that essentially shrinks the feature. Shrinks the feature coefficients exactly to zero. And what does this mean? It means that it effectively removes those features. So if a feature isn't pulling its weight, so to speak, Lasso will eliminate it entirely. And so this gives you a simpler model with only the most important features. The other one is the L2 regularization, or RIDGE. And so this adds a square magnitude penalty that shrinks coefficients towards zero. So instead of removing features completely, like with L1, it reduces their influence. So features become less important, however, they still stay in the model.
That is very interesting to know about. So, Anieka, how about we take a look at the demo? Any suggestion of what we might
I
you
can't
might want to
wait.
look at?
We might want to get into SageMaker. And
SageMaker. All
yes.
right.
So yeah.
SageMaker it is.
All
All right.
right.
So let me go ahead and add my screen here. There we go. All right. So let's look at a demo inside SageMaker. And I am actually here inside Data Wrangler, folks. So what you see here is a data flow. I imported a synthetic that I generated, really synthetic data set for e-commerce data from CSV. And then as you see here, I have run it through a number of different transformations. So it's kind of a long data flow, but that's what we're looking at. And in particular, what I wanted to show you is I wanted to show you some techniques and transformations that I applied here that are relevant to our conversation about feature engineering. So again, this is the data set, and I even generated some columns here. So there are a lot of different transformations, but the one I'm going to focus on is going to be specifically those that are, again, more relevant to our conversation about features.
So Eva, we are looking, sorry to jump in, we're looking
Yeah,
at a tabular data, right? And so we have these columns of data,
correct.
multiple dimensions. Okay, so regular tabular data set. Okay, and we can easily identify these features. Cool. All right.
Exactly. And actually, let's just point out here that what we have here is these are our features, right? These are our features. Can you still see my screen okay?
No,
Okay, I
you
thought it looks like it
wait.
might have dropped off. So let me bring it back 1
Okay.
second. No worries there.
Yeah. So yeah, in that tabular data set, we saw different features, and we're able to the model or the algorithm, whatever
Like
we're
right
doing, or
here.
whatever method we're going to be using, will essentially transform those categorical data into numerical format.
Exactly. And Aniek, could you please confirm you can see my screen again?
Yes, I can.
Great, thank you. Yeah, so again, those are the features. And so let's take a look here. I have a couple different, like I mentioned, transformations that are relevant to our conversation about feature engineering. The first one here, a custom formula, is where I actually created a new column called spending segment. Let's find it here somewhere.
And is that column a new column, or is that did you combine uh, other columns
Yeah,
in some
great
way?
question. So this was actually a new column, and I generated with a formula where it will be a little hard to see here, but I'll try to show you. So I took the existing column of purchase amount, and then if the purchase amount was greater than 300, then I generated a high spender value, whereas if it was less than, then I generated, medium or low. So that's how I populated this column. But this was a
Interesting.
brand new column that was generated here with this formula. So that's one thing
Interesting.
we can do: create new columns if they're, if we think they might be helpful for our um, model
Yeah,
prediction.
exactly. That's what I was going to say. You did it because you have some domain expertise around the data, and you felt you needed this adding this new column or this new feature would help with better getting better predictions.
That's exactly right. Absolutely, Anieka. The next one to show you here, I'll just show you a couple more, is the one hot encode, because I know, Anieka, you just talked about it, right? So here I have three that were categorical columns: gender, location, and the spanning segment. And as we learned, they need to be turned into a vector of some sort, numerical, so that the model can understand them. So what I did
Hmm.
here is simply say, I would like you to apply the one hot encode to those three columns. And
Hmm.
after this was applied, so here's, for example, the gender, you can see. This is what it looks like, folks. So these are the one hot encoded vectors. And without maybe going too deep into it, I'll just point out here, if we take one of those, this is going to represent basically a sparse vector with 4 possible categories for gender. So female, male, maybe some other one, maybe unknown. And then it's also going to tell us, like, the index of 0 would be male, let's say, female, and so on. But this is what a hot encoded categorical variable is going to look like right here.
Okay.
And so this was the one hot encoding. Let's see, what else
And
can
the
I
one
show
hot
you here?
encoding did increase the number of dimensions for your data set, right? Because we're
That's
taking.
actually, yeah, that's actually a great point. And that is exactly the case. It's going to increase the number of dimensions because it converts categorical columns into multiple binary columns, and then each category is going to become its own column. So
Right.
the number of columns is going to really be the number of unique categories.
Right. And what's the impact of that? What's the impact of increasing the number of columns, number of features in your data set that way?
Yeah.
Especially if you have a lot of those columns that you're using one hot encoding on.
Exactly. So this is going to result in increasing dimensionality, right? And again, that's more columns, more features, high dimensionality. It can impact the performance. So definitely, it's something
Okay.
to keep in mind and consider as far as the approach. But that is the result of
Okay.
one hot encoding. Great. And let me just show you one other one here. I think I have one more custom formula. Actually, a couple other things I wanted to show you. Let's see. Actually, here I was just generating a new column because I had somehow inadvertently converted the age with the min-max scaling, so I wanted to bring it back. So that
Mm.
was what was going on here. Let's see.
Okay.
Yeah, so you get the idea. You can also drop columns, right? And things like that. So all this is through a visual low-code interface through Data Wrangler. And
Mm.
let's take a look at the analysis as a last step here to show you. So here I've used the quick model feature of Data Wrangler, and I have a classification problem. I want to classify if the data set is going to have a purchase made, yes or no, right? And so I generated the quick model here, and it's a little hard to see. I'll try to zoom in a little further, but basically those are going to be the available features, and then it's going to rank their
By
importance,
importance.
right?
Interesting.
Yeah.
Okay.
So according to this quick model, and again, that's a quick model, keep that in mind, it looks like the items viewed was the highest, the most important feature, but it's only 0.14 on a scale 0 to 1. So what that suggests is that there are actually several columns. So abandonment rate, cart abandonment rate, or purchase amount, they seem to be pretty high as well. But it's really helpful to see here which features are most important for your model. So that's what
Yeah.
I wanted to show you, folks. Anything to add, Anieka, here? Or
Yeah. Yeah, this importance, this is used by lots of different techniques. For example, whether if we go back to talking about the L1 and the L2
yeah,
regularization, that takes that into account. That takes the importance of the features into account. So, like for example, the L1 regularization might eliminate less important features altogether. So yeah, that has an impact down the line. Very cool.
Absolutely. Actually, there's one thing I wanted to add. So we saw a demo of Data Wrangler. Just want to bring to your attention for the exam for one other feature that is relevant, which is the SageMaker Feature Store.
Yeah.
That's another one. We're not necessarily going to demo it today, but be aware that the SageMaker has a feature store feature, which is also used for feature engineering and storing features.
And with Feature Store, there are two types of feature stores, right? There's the online and the offline feature store, right? When would you use?
Okay. Actually, that's good to know for the exam. So I'm glad you brought it up. The online feature is going to be for low latency access. Really, if you need to serve a feature in real time for real time inference, would be I guess the term. And then you have an offline, which is best for batch access and for training data. So you can use both in real time, and you can share features between different models and things like that.
Very cool. Very cool. Once again, great demo. Really helpful. This is why it's really good to be able to get hands-on experience, because even just what you just showed us today exposes a lot of the things that we have been learning about and reading about, and seeing it in action. It really helps put things together.
My pleasure, Yakan. Yeah. All right. So I think this is a wrap. So thank you all for watching, and thank you for liking and subscribing. Till next time.
Till next time. Thank you, everyone.
Bye.